Assalamualaikum warahmatullahi ta'ala wabarakatuh. Bismillahirrahmanirrahim. In the last chapter, we have looked at properties of fluid. In this chapter, we looked at fluid static, which is fluid which is not moving. It is important for us to learn about the physics of static fluid because fluid will exert pressure, and we know that pressure is actually force divided by the area. So any surfaces which are in touch with fluid, whether it is actually stationary or moving, will be subjected to this force. For example, if you have a dam or fluid gate, the dam surface will be subjected to hydrostatic pressure. So we have to make sure that the dam structure, for example, is actually strong enough to withstand this hydrostatic force due to fluids. Hence, it is very important for us to know, first of all, the magnitude of this hydrostatic force, and secondly, the directions at which this hydrostatic force is acting. So in this chapter, first of all, we looked at fluid pressure at a point, and then we will define absolute vacuum and gauge pressure. Then after that, we looked at the formula that gives us how pressure varies with elevations. Then after that, we looked at pressure measuring devices, barometer, which is an apparatus to measure the atmospheric pressure, and then apparatus for us to measure pressure in general, which is open-end manometer, differential manometer. Then we looked at a paradox, which is called hydrostatic paradox. And then continuing from there, we looked at hydrostatic force on submerged surfaces. First of all, we looked at plain or flat surfaces. Then after that, we looked at hydrostatic force on curved surfaces. And then we closed the chapter by looking at buoyancy and stability of immersed and floating bodies. Fluids in general will exert both normal and shearing forces on any surfaces that the fluid is in contact with. Shearing force will produce only when there is relative motions, meaning that when the fluid is actually flowing. Without the relative motion, only the normal force or direct force will exist, which is called pressure forces. No relative motion here not necessarily means that the fluid is absolutely stationary. It can also mean fluid which is moving with the same constant velocity, or fluid which is moving with the same but varying velocity. For example, it is moving at a constant velocity profile. So that is still considered as static fluid. First, let us consider fluid pressure at a point. Let's consider fluid. So this is the surface. And let's consider element of the fluid at this point here. And for the sake of analysis, let's consider an element which looks like a wish. So consider a fluid element of wish shape. So let's draw the element. So I'm going to call this direction as X, this is Y, this is Z. So this is my delta X, this is my delta Z, so this is my delta Y, and let's call this slanted distance delta L. So if this angle is alpha, so delta X is equal to delta L cos alpha, and delta Z is actually equal to delta L sine alpha. And let's say this surface here, let's call that one delta A. So now let's consider the hydrostatic forces acting on these surfaces. Hydrostatic force will act perpendicular to the surface and towards the surface. So here, perpendicular directions, Pn multiplied by this area, so Pn delta A. In upward directions on the bottom surface, equal to P in the Z directions, multiplied by delta A, but the component of delta A on the bottom surface is delta A cos alpha. Then the hydrostatic force acting here is the forces in this direction, so Px delta A sine alpha. Then there is one more force component, which is due to A is equal to mg. Since the fluid is in equilibrium, we can balance the forces in any directions. Let's balance the forces in the x directions. So balancing forces in x directions. So the forces in x direction, first of all, in this direction is Px delta A sine alpha, and that will be balanced by the x component of this force here. So if we draw the force triangle for that, so this is alpha, so this is Pn delta A acting that way. So this is Pn delta A sine alpha, and this is Pn delta A cos alpha. So in the x directions, Px delta A sine alpha is exactly balanced by Pn delta A sine alpha. So sine cross and A cross. So here we can write Px is actually equal to Pn. So next, we balance the forces in the vertical directions. So balancing forces in z directions. So the force upward is due to Pz delta A cos alpha. So we can write Pz delta A cos alpha. And the force downward, first of all, will be due to component of this in the downward direction, which is Pn delta A cos alpha. Plus, there will be this component of weight, mg, which is also acting downward. But what is m equal to? M is actually equal to rho multiplied by the volume. So it's actually rho multiplied by volume will be half delta L cos alpha. So half multiplied by the base and multiplied by the height delta L sine alpha multiplied by this here. So delta y, which gives us half rho delta L delta y is actually equal to delta A delta L cos alpha sine alpha. So we substitute in this equation here. So we have Pz delta A cos alpha must be equal to Pn delta A cos alpha plus half rho delta A delta L cos alpha sine alpha t. So delta A will cross, cos alpha will cross. So we can write Pz is equal to Pn plus half rho delta L sine alpha t. So as delta L tend to 0, so this will go to 0. So we can write Pz is actually equal to Pn. So just now we have Px is equal to Pn. So now we have Pz is equal to Pn. So this, now we can write Px is equal to Pz is equal to Pn. So basically, the forces act equally in all directions. So we can conclude that at any point within the fluid, pressure is acting in all directions equally. And there is a name for this law. This is actually called Pascal's law. And this conclusion is also applicable even if there is relative motion. Due to Pascal's law, in a closed system, the pressure change produced at any one point in the system will be transmitted throughout the entire system. And this is actually the principles of hydraulic lift. So if we have a closed system, so let's say closed systems that look like this. Let's say we consider 2 points, point A here and point B here. Because of the fact that the pressure at A is equal to the pressure at B, we can actually write PA is equal to PB. Then if this area is equal to AA, and this area is actually equal to AB, since PA is equal to FA divided by AA, then PB is FB divided by AB, where FA is the force applied here, and FB is the force applied here. We can write this equation here. So we can write FA is equal to FB AA over AB. So this is the basic principles of hydraulic lift. If the ratio of AA over AB is small, that means that the force that you need to apply at A will be reduced by the ratio of AA over AB compared to the force which is applied at point B. Let's look at this one example related to hydraulic lift. So in this problem here, a hydraulic jet has dimension as shown in the diagram. If one exerts a force of 100 Newton on the handle, what load F2 can the jet support? So what will be the load F2 that the jet can support? Neglect the lifter's weight. This is the lifter. Let's first of all draw a schematic diagram. So we have a and this is the piston, and this is the lifter. Then the piston is connected to an arm and its hinges here. Given that the diameter of this is equal to 5 centimeter, and then the smaller pistons has 1.5 centimeter diameter. And given that the distance from here to here is 3 centimeter, then from here to here is 30 centimeter. And the force F is applied here. And this is the load F2 that we want to calculate. So the question says that if force F is equal to 100 Newton, what load F2 can be supported? So first of all, let's consider free body diagram of the arm. So let's consider free body diagram of this. So if we draw the arm like that, it's hinged there. So the force F is being applied there, and then as we apply the force here, there'll be equal and opposite reactions. So the force is there, call that one is equal to F1, and let's call this arms R1, and then this arm here is called R2. So it's hinged here. So what we can do, we can balance moment about hinge. That gives us F1 R1 must be equal to F R2. So this allows us to get expression for F1 is equal to F R2 over R1. Next, let's consider the fluid pressure. So the fluid pressure here is the same as the fluid pressure here. So we consider the liquid pressure. So if I redraw And I call this point here A and this point here B. So the force that is being applied there is equal to F1, and the force which is being applied here is actually equal to F2, which we want to find out. So we can say that PA is equal to PB. So PA is equal to F1 over A must be equal to F2 over AB. So we can get F1 is equal to F2 A1 over A2. So now we get the expression for F1 here, which is equal to FR2 over A1, and then the expression here, which gives us F1 is equal to F2 A1 over A2. So we substitute F R2 over R1 is equal to F2 A1 over A2. So in order to calculate F2, so F2 is equal to F R2 over R1 A2 over A1. So this gives us the force is 100 Newton. So 100. R2 is this distance here. So this distance here is 30 plus 3, so 33 cm. R1 is 3. And then area of A2, the diameter is 5. So it's 0.05 squared divided by 0.015 squared. The pi parts cancel with each other. So that gives us 12.222 kilo Newton. So we can see that by applying a force of 100 Newton, we can actually raise weight of 12.222 kilo Newton. Pressure is normally measured as pressure difference. Pressure above absolute vacuum is called absolute pressure, whereas relative pressure above atmospheric pressure is called gauge pressure. And relative pressure below atmospheric pressure is called vacuum pressure. So if this line represents absolute zero, P is actually equal to 0 Pascal, then this line represents P ATM, where P is equal to 101 kPa, and let's say pressure at A here, PA, which is equal to 301 kPa absolute. So the height of this is 301 kPa. So the relative difference between PA and PATM, which is equal to P gauge A, and that's equal to 301 minus 101, which is 200 kPa. So we can say that PA is equal to 301 kPa absolute. It is also equal to 200 kPa gauge. So let's say PB. PB is here. So PB is equal to 51 kPa absolute. So we can define, so this height is equal to 51 kPa, and the difference between PATM and PB, whereas PB is actually lesser than PATM, So P gauge at P is equal to 51 minus 101 equal to minus 50 kPa gauge, and it's also equal to 50 kPa vacuum. So we can write PB equal to 51 kPa absolute, and it is also equal to 50 kPa vacuum.